Hey, Linux wizards. Ready to conquer the cloud? Today we are diving into the wild world of cloud computing. Now, cloud networking can be a beast with many heads. Think AWS, GCP, Azure, but we are starting with Google Cloud Platform, GCP. Why GCP? Because its approach has some unique twists compared to others. In this video, we'll unlock the secrets of GCP's Virtual Private Cloud VPC. We'll explore its features and superpowers and the problems it solves. This is just the first step on our cloud networking journey. Want to see how we design a rock-solid VPC for multiple applications across the globe? Then smash that subscribe button and hit that notification bell. My name is Philip and let's get nerdy. Imagine this. A company starts small with just a single server rack humming away in their office. But as their business thrives, so does their need for computing power. They add more and more racks, filling entire data centers. Soon, one data center isn't enough. They expand to new regions, then continents, building redundancy and reaching customers worldwide. Then a groundbreaking idea emerges. What if they could utilize this massive infrastructure to help others? This is where cloud computing takes center stage. Cloud providers like Amazon, Microsoft, and Google saw an opportunity to offer their infrastructure, servers, storage, and network as a service. This service model is called infrastructure as a service. With infrastructure as a service, you essentially rent virtualized computing resources over the internet. Think of it as your own self-service data center where you pay only for what you use. You can get access to virtual machines, storage, and networking infrastructure, all managed by the cloud provider. You, however, maintain control over the operating system, applications, and development frameworks you use. Just like your home or office network relies on physical switches and routers, the cloud utilizes a virtual network. The virtual network, built on top of the cloud provider's physical network infrastructure, is what allows you to manage your resources securely. Here's where things get exciting. This virtual network infrastructure is called a Virtual Private Cloud, VPC. A VPC empowers you to create your own customized network environment within the cloud. You can define private IP address ranges, create subnets for specific purposes, set up security rules like firewalls, and connect your cloud resources securely. But before we delve into the problem VPC solves and its various features, let's actually create one and see it in action. I have a project created and command line access enabled. If you'd like to see how it's done, please let me know in the comments. To create a VPC, I will use gcloud compute networks create command and provide the VPC name. I will name the network VPC test as it will hold our test environment. You can have more than one VPC in your project, so make sure to name it something meaningful. This command will create a virtual private cloud in our project. Here we go. There's our VPC. I'll talk about subnets and subnet mode in a second. First thing to note is that VPC is a global resource. It spans across all regions. It holds a single routing table for the entire VPC network. This table specifies how packets are routed to their destination based on IP address ranges and next hop information. At the moment, we only have the default route that essentially provides a path for your VMs to connect and communicate with the external world. However, in order to deploy a resource within a specific region of your Google VPC network, we need to create a subnet in the desired region. Subnet is a regional resource. It exists within a specific region of your VPC network. Here's the list of available cloud regions where we can create our resources. I'd like to have my resources in the States, in Iowa, that's US Central 1, and Warsaw, Europe, that's Europe Central 2. Let's start with creating the first subnet. I will use the gcloud compute network subnet create command, followed by the subnet name. Let's make it something meaningful. I will name it net for subnet, then the environment. We are working on VPC test, so let's put the test and then the region name. Just by looking at the name, we can figure out that it's a test subnet in US Central 1 region. Next thing we need to provide is the VPC this network belongs to. Let's put VPC test. Also, let's specify the region as US Central 1. Subnet needs to have a range of private IP addresses set. I will then assign IP addresses from the range to the resource. Let's set it to 10.200.00/20. I will explain the reason behind it in a second. Lastly, let's enable private IP Google access for the subnet. Basically, what it does, it allows access to Google Cloud API from this subnet for instances without a public IP address. Okay, our subnet in US Central 1 has been created. Mind that it's IPv4 only. We'll talk about IPv6 in a different video. To explain the reason for this specific network, we did choose 10/8 network as that's the largest private network we can use. .200 indicates it's a test network, so everything that starts with 10.200 will be a part of our test VPC. Then we have 00/20. /20 has over 4,000 IP addresses. That's a reasonable default for number of instances. Mind that the last address of the subnet is 10.200.15.255. Let's create a new subnet for Europe. I will name it accordingly to our naming convention as net test Europe Central 2 and set the range to 10.200.16.0/20. Mind that the subnets within VPC cannot overlap. Hence, we did assign a new block of 4,000 IP addresses right after the first block. We have two subnets, each in different region, each having their own network range, but both coming from the same 10.200 network. If we look at the routing table, we'll discover that two new routes to our subnets have been created. What we've learned so far: Google Cloud VPC is a global resource. Subnets are regional resources. Each subnet needs to have its own non-overlapping block of private IPs. Whenever you create a new subnet, it will auto-create a route in the VPC routing table. The primary function of VPC is to enable connectivity between your virtual machine instances deployed in various regions. If we look at our VPC, we see that the subnet mode is set to custom. We did request that during VPC creation. By default, GCP creates a subnet with a predefined IP range in each region for your VPC network. This is called an auto subnet mode. To maintain granular control over subnet creation and IP allocation, we opted for the custom subnet mode. Let's see some action and deploy some instances. To do that, let's talk about regions and zones. Each region consists of several zones, usually 3 or 4, geographically separated within the same area. A zone is an independent data center. Usually, the distance between zones is between a few to tens of kilometers. This translates to latency in range of milliseconds. Let's list the zones for US East 1 region, that's South Carolina. There are 3 zones available. In other words, 3 data centers within that region. I will create an VM instance and name it VM1. Let's specify the zone we want the instance to be created as US East 1B. Machine type as E2 micro, that's a tiny VM. Oh, it failed. We need to specify the subnet for the VM's network interface. Unfortunately, we don't have any subnet in that region. Thing we've learned is you cannot deploy a VM in a specific region if there is no subnet in that region. In such a case, let's list zones in regions that we did create a subnet already. US Central 1, Iowa. There are 4 zones available. Let's create a VM, but this time I will set the zone as US Central 1A and specify the VM network interface should be attached to a subnet in that region. Okay, our instance has been created in US Central 1, Zone A, and the private IP has been assigned from the net test US Central 1 subnet. Let's create another VM in the same region but in a different zone. I will pick US Central 1 Zone B. Okay, we see both VM1 and VM2 running. Important thing to mention is that despite those instances being in separate zones, separate data centers within the region, they still belong to the same subnet. This concept is totally different from AWS, where each zone has its own subnet. In GCP, a subnet is spread across all zones in a region. Let's try connecting to VM1 as it has a public IP assigned. There's a handy command that performs exactly that. SSH connection to the public IP of the VM. We just need to provide the instance name and the zone. The connection failed with a timeout. Why is that? Here we come to the second feature of VPC. First one is connectivity and routing. Second one is distributed firewall that filters incoming and outgoing traffic at the network level. This means that traffic entering or leaving the network is inspected against a set of predefined rules. These rules, called firewall rules, determine whether to allow or deny specific types of traffic based on criteria like protocol, source and destination IP address, ports, and more. By default, all incoming traffic is denied. In such case, let's create a rule with gcloud compute firewall rules create. Let's call it home SSH. The VPC it applies to is VPC test. The direction of the traffic is ingress. In the source range, we'll provide our home IP. As the traffic type, we'll mention TCP port 22 for SSH. And finally, the action is allow. That's a pretty basic rule. Mind that we did not specify the destination. In such cases, it will apply to all VMs in our VPC. Whitelisting static IPs is not the best and future-proof way to design our firewall. There are much better ways to do it. Today we are just doing a minimum firewall setup to demo some VPC concepts. We'll talk about instance access and firewall design in one or future videos. Let's try logging into our VM again. This time it worked. We are in. Mind that by default, the outgoing traffic is allowed. So if we try accessing the internet from our VM, it will work as our VM has a public IP. Our firewall is stateful. This means that when a connection is allowed in one direction, the corresponding return traffic is automatically permitted. GCP distributed firewall offers some interesting advantages compared to traditional firewalls. Because it's integrated into the VPC layer, it's inherently distributed and scales with your network. This eliminates the need for separate hardware and simplifies the management. Let's connect to the second instance, that's VM2, and check its IP. It's 10.200.0.3. Let's check the IP of VM1. It's 10.200.0.2. I will try pinging VM2 from VM1. It does not work, but why is that? While firewall rules are defined at the network level, connections are allowed or denied on per instance basis. So, every time traffic enters a VM, the network layer validates if it's allowed. We need to allow instance to instance connectivity. In such a case, let's create a broad rule that accepts all incoming traffic from the whole 10/8 private network. If I retry the connection test one more time, it works. First thing to note is the latency between the VMs is around 1 millisecond, despite those VMs being in separate zones, separate data centers within the region. Another thing to mention is that the instance has a /32 mask. So it only sends packets to the default gateway's MAC address. And then Google Cloud forwards the packets to the destination IP address within the respective network. If we look at the ARP cache, we'll discover there's only the MAC address of the default gateway. Mind that the default gateway is a virtual IP address, not a physical network device. It doesn't respond to ICMP requests and isn't designed to be directly reachable. Moreover, the GCP network is unicast. It does not support multicast or broadcast. Unlike traditional networks where devices might use ARP requests to discover neighboring devices, in GCP, the VPC code determines how to forward packets to the correct location. VPC holds MAC lookup tables, IP lookup tables, and active connection tables that cannot be inspected. So long story short, all packages go to the default gateway's MAC. That in turn decides if the packet should go to the same VPC, peer VPC that we'll talk about in the next video, or go to an external location. If the destination is external, it's the VPC code that will rewrite the header by placing the external IP as the source Information about mapping between private and public IP are stored in the IP lookup table in the VPC. The SDN layer will also record the packet in the active connection table. Once the response gets back, those tables are consulted to check if the reply is part of an active connection and which private IP to send the reply. Instance with a public IP is just one of the options to access the internet. We'll talk about other options in a separate video. There's one more thing I'd like to show you. You can have more than one subnet in a region. Let's add a second subnet in US Central 1. If we look at our subnet list, we'll see two subnets in US Central 1 region. Let's create an instance named VM3 in that third subnet. Now let's try pinging VM3 from VM1. Despite VM3 being in a separate subnet, the connectivity is there. It looks as if those VMs were on the same network segment. This is just how /32 and smart data forwarding in Google VPC works. Multiple subnets in a region may become handy if you run out of IP addresses. To close the topic of connectivity within a single region, let's briefly talk about pricing. It's a pay-as-you-go model, we know that already, but in general, incoming traffic is free of charge. Of course, excluding any services like load balancers, proxies, VPNs, and so on that are charged extra. You only pay for outgoing traffic. Traffic within the same zone is free of charge. However, traffic between zones within a region is not free. We know that we need a subnet in a region to deploy a VM. We also know that we can have one or more subnets in a region and that each VM can directly talk to any other VM within the same or different subnet in the region as long as they are part of the same VPC and the firewall allows the traffic. Let's go one step further. I will create a VM in a different region. We have subnets available in US Central 1 and Europe Central 2. Let's create VM4 instance in Europe Central 2 Zone A, where the network interface is part of net test Europe Central 2 subnet. If we look at the list of our instances, we have 3 VMs in various zones of US Central 1 and a single VM in Europe Central 2 Zone A. Let's try connecting from VM1 in US to VM4 in Europe. Do you see that? It works. Moreover, those two VMs seems to be directly connected. This is an amazing concept. It provides great connection flexibility, unlike AWS, where the VPC is regional, and in order to connect two regions, you need to have two VPCs created and establish a peering connection between them. In GCP, VPC is a global concept and allows you to very easily connect instances across the world. If we look at the latency, it's around 120 milliseconds. You can check the median latency between region pairs by going to the latency dashboard of the GCP console. Mind that the price of traffic between regions is higher than between zones. We've scratched the surface of GCP networking today. We haven't covered secondary IP ranges, dual stack subnets, proxy subnets, cloud routers, cloud NAT, load balancing, VPNs, high availability, or even more advanced firewall configuration and network design. But fear not, those exciting topics will be explored in future videos. If you enjoyed this intro, hit that like button and subscribe to stay tuned for deep dives. Thanks for watching.